So good afternoon, everyone. Thank you for being here. Thank you again, Wilson, for accepting our invitation. So today's Priberam Machine Learning lunch seminars will be about explainable AI, and in particular applications of explainable AI to the support of medical diagnosis, where these algorithms are particularly important. And to speak us about this topic, we have Wilson Silva, who is a PhD candidate at the University of Porto and a research assistant at INESC TEC. He is also a teaching assistant at the same university, and his main research interests include machine learning and computer vision, particularly when applied to explainable AI and medical image analysis. So Wilson, when you're ready, please, you can start.
Okay, so hi everyone, and thank you Diogo and Priberam for the invitation. So I will just start sharing my screen. So let me, sorry. Okay, so are you seeing my screen?
Yes.
Okay. Hello everyone. My name is Wilson Silva, and I'm going to talk today about explainable AI and its role in supporting medical diagnosis. So just a little bit of my background to start. I have an integrated master's degree from the University of Porto. During my master, I was a visiting master student during 1 year at the Karlsruhe Institute of Technology in Germany. My master thesis was on software-defined radar for medical imaging. So it was, at that time, I was not working in machine learning. I was working in a completely different field. And in between my two academic experiences, I was an IT advisor at KPMG Portugal in Lisbon. So now more in terms of research context, as Diogo said, I'm currently a PhD student in electrical and computer engineering, basically machine learning and medical image analysis at the University of Porto. And at the same time, I'm an invited assistant at the Faculty of Engineering. My PhD supervisors are Professor Jaime Cardoso, who is a full professor at the University of Porto, and Professor Maria João Cardoso, who is the head breast surgeon at the breast unit of the Champalimau Foundation. And during the PhD, I was also a visiting student at the University of Bern and at the Inselspital, the Bern University Hospital, where I collaborated with Professor Mauricio Reis and a radiologist, Alexander Pollinger. So now starting discussing the work. So today I will provide like an overview of part of the PhD work that I've been doing in the last 4.5 years, mainly related to explainable AI. And I guess almost all of you already know that explainable AI is something that is really necessary, particularly in the clinical field. Because what is happening today is that clinicians and particularly radiologists face an excessive workload, and that may contribute to an increase in the amount of undesired diagnosis mistakes. And something that could be really helpful is to have decision support systems to help the clinicians make the decisions. However, most of the works that have been proposed and that are quite successful are very complex algorithms like ensembles and deep learning algorithms, and their clinical use is hindered by their lack of interpretability. So explanations are really needed to understand these algorithms, and my proposition is that more than that, they could be useful to also support the decisions. So the work that we have done was mostly around the generation of what we called complementary explanations. So having kind of multimodal explanations.
Sorry, Wilson, just sorry for interrupting you. I don't know if it's supposed or not, but the slides, we are not seeing them change. They are still in the cover slide.
Okay, sorry. So I will, no, it was not intended. I will start sharing again, sorry. What about now?
Now it's fine, yes.
Okay. Okay, so I was basically in this one. Okay, so as I was talking about, so we were mostly focused on trying to generate complementary explanations, so kind of a multimodal explanations, and one of these type of explanations that we were really focused on was case-based explanations. And we mostly worked in these three clinical applications. So the aesthetic evaluation of breast cancer treatments, which was the main motivation for my PhD work, but also melanoma detection in dermoscopic images, and more recently, pleural effusion diagnosis in chest X-ray images. So, like the first work that we developed in this explainable AI space, we start by using as input features some high-level clinical concepts that were defined by clinical experts as inputs to our deep neural network. And the reason for this was not to make it simpler, even though it's true. It was because like the applications that we were focused on were really difficult. It was really difficult to have a good performing model in those applications. So we started with some prior knowledge, clinical knowledge that we already had. And regarding this search for case-based explanations, we basically start by exploring the semantic features close to the decision space so that we were able to find meaningful and representative explanatory examples. And so here I present the first model that we used. It was a deep model that included some monotonic constraints to make it more interpretable. And what we did with this model was, besides classification, we also tried to generate these complementary explanations to try to please all types of explanation consumers, starting from the idea that there are people that prefer verbal, like rule-based explanations, and there are others that prefer more visual case-based explanations. And as I previously mentioned, the input to this network were high-level clinical concepts that were defined by clinical experts. And this network had two branches, and the reason for that was that for some of the high-level features, we knew that they had a monotonic behavior with relation to the output, but for others, there was not that monotonic relationship. But we kind of tried to convert them in monotonic features in a semantic space, and that's why we also have the monotonic constraints in the final layers. And this work was presented at the IMIMIC, which is a workshop in interpretability of machine intelligence on medical image computing at MICI 2018. So now to describe a little bit in more detail what type of features are we talking about. So this network, we applied to these two applications, so to the aesthetic evaluation of breast cancer treatments and also to melanoma detection. And we use these two data sets. So the BCCT, which means breast cancer conservative treatment data set, which had 143 images with 4 original classes, so excellent, good, fair, and poor. and also 23 features describing symmetry measures and differences in color, like global differences in color that we call color measures, and also local differences which we called scar measures. And in terms of the PH2 data set, it has 200 images, 3 classes originally, and 14 features describing the presence of certain colors and also abnormal patterns like dots and sticks. And as I was saying, so initially we were really focusing on trying to have complementary explanations. So trying to have different types of explanations to try to please and convince all types of explanations consumers. And one of these types was what we called explanation by local contribution, where we try to generate a rule-based explanation to justify the decision. And here we also balance the contribution of each feature to try to increase the diversity of the explanations. Otherwise, we could have just one feature explaining everything. And besides this more rule-based explanation, we had these case-based explanations that at the time we called explanation by similar examples. And here we tried to have a kind of factual explanation where we looked for the nearest neighbor from the same class and tried to find out what made them similar, and also a kind of counterfactual explanation where we looked to the nearest neighbor from the opposite class and tried to find out what made them different. And at the end, we have explanations like the ones I'm showing here. So for a given input image, I must say that so this network was used for a binary classification problem. So in the original problem of BCCT, we have 4 classes, but we just considered like several binary classification problems. So excellent versus all the others, or excellent and good versus full and pair, which is exactly the case that I'm showing it here. And so like for a given input image, I have a prediction, and I also have a rule-based explanation given by the local contribution study, and also 2 case-based explanations, one factual, one counterfactual, and the same for the melanoma detection problem. So another thing that we proposed in this work, and it's quite important, and so now there are more frameworks to evaluate the quality of the explanations, but at the time there were just a few, and still nowadays there is no like clear way that everyone uses to evaluate the quality of an explanation. Typically, this is done in a qualitative way more than in a quantitative way. But in this work, we also proposed these proxy functions that we consider measure the quality of an explanation, and we call this approach the 3 C's of interpretability, and they are completeness. So an explanation should be applied to more than just one case, so it should be applicable to a certain number of cases. Correctness, so an explanation, if we consider an explanation as a model, it should be accurate, it should allow us to classify, and also compactness, so an explanation should not be too large, otherwise it's not an explanation, it just doesn't explain anything. And this framework could be applied both to rule-based explanations and also to case-based explanations. So here I'm just presenting the quantitative results of the proposed model, both in terms of prediction quality and also in terms of explanation quality, measured by these three C's of interpretability. And we compared our model with a simple rule-based model, it's a decision tree, and also with a simple case-based model, a nearest neighbor. And as you can see, our model was able to outperform the other 2 in both classification performance and explanation quality in general. And basically, so at this point in time, we were really focused on having diversity of explanations and on having these complementary explanations, as we call it. So the next step was moving from a deep model to an ensemble model, which is the other type of model that is very complex and allows to obtain very good performances. And so the ensemble model that we proposed is the one that you can see here on the right. And it's basically composed by the deep neural network that I presented before, but also by a scorecard, which is a very interpretable model commonly used in finance, and a random forest, which in itself is an ensemble model, an ensemble of decision trees. So in terms of classification, we use just a majority voting of these three models, but we were really focusing on obtaining diversity of explanations, and that was given by using the case-based explanations generated by the deep neural network, and by having rule-based explanations generated both by the scorecard and the random forest. But besides diversity, we wanted to have like a unique explanation for the ensemble. And for that, we came up with this equation that is presented here, where the explanation of the ensemble is the explanation given by the model that agrees with the ensemble, and at the same time maximizes the correctness of the explanation. And by correctness, I mean the correctness that I described before in the 3 C's of interpretability. And again, just looking to the kind of explanations that were generated. So for a given image, we have a prediction, this time the prediction of the ensemble, and we have these 4 explanations. So we have a rule-based explanation given by the random forest, and a rule-based explanation given by the scorecard, and then the 2 case-based explanations given by the deep neural network in the same way as done before. And so now looking to the more quantitative results, and as you can see, the ensemble leads to a best classification performance, what was expected, and it's also quite competitive in terms of explanations, in terms of explanation quality. Okay, and so this kind of summarizes the first line of work, which was more focused on producing complementary explanations. So trying to have diversity, trying to have rule-based and case-based explanations to try to justify and help the clinicians in their diagnosis, or in the case of aesthetic evaluation, in the quantification of aesthetics. And then I moved to Switzerland. And in Switzerland, I collaborated quite closely with a clinician, with a radiologist. And after some discussions, it seems that the clinicians are not that interested in having a label, so in having the prediction, but they are more interested in kind of retrieval systems. So basically, when having a case under analysis, what they typically do when they are in doubt is to search for past cases that are quite similar to the one being analyzed to help them make the diagnosis. And what we found out was that most content-based image retrieval systems are not helpful in this context, because they do not consider the fact that relevant information in the medical scenario is typically spatially constricted. And so what we did was to try to use interpretability saliency maps to localize these relevant regions in a weakly supervised manner, trying to lead to more focused representations, therefore improving a medical image retrieval and being able to present the most similar images in terms of disease and not the most similar images in general. And this work was presented at MICAI 2020. So the approach was actually quite simple. So we call this approach interpretability guided content-based image retrieval, and it consisted of a two-step training process. So in step one, we just trained like a common CNN disease classifier. In this case, it was a DanceNet, to try to diagnose, in this case, pleural effusion. And after this step one, we use these saliency maps that were generated after the training of the first model to then fine-tune the model. And after having this fine-tuned model, we then looked for the semantic features close to the decision space, and then just computed the Euclidean distance to find which cases were the most similar to the one being analyzed. And so we performed 5 experiments with this, corresponding to 5 different sets of images. So for any given query, we had catalogs of 10 images, and those 10 images were ordered by a board-certified radiologist, and we then compared the different methods with the ground truth given by the radiologist. And for this comparison, we basically used like a traditional similarity computation, like the structural similarity index, and also the CNN resultant from step one of this approach, so a normal classifier. And then we measured the quality of this retrieval system by using the normalized distance cumulative gain. And as you can see, it follows much more closely the order given by the radiologist than the other methods. And here, just to present some more visual results. So here we are basically presenting the top 4 retrieved catalog images for one query image that was classified as, that was labeled as having pleural effusion. And in the first row, you have the ranking provided by the radiologist. And then in the second row, the results given by the structural similarity index, then the CNN base, which is basically step one, and finally our approach, which, as you can see, follows quite closely the ranking of the radiologist. So to summarize this work, this approach leads to a better similarity measure between medical images, and that leads to a better image retrieval. And we can also say that it enhances the interpretability as it accompanies the retrieval with some visual explanation. So you can see the ranking, and you also have the saliency maps that provide you kind of an attention image of what is being what the network is focusing on. But of course, the quality of the retrieval is limited by the classification performance. So if you have a bad model, your retrieval will also not be that good. So following this line of work, or if we want to follow this line of work and basically try to support decisions by presenting case-based explanations, there is one type of problem that could arise, and that is exposing identity. And that is not a problem when you are just analyzing images in the hospital. But for instance, if you want to use a system like this one to teach medical students, or if you want to use a system like this one in a medical data sharing app like Tonic app, for instance, then you will have a problem because you are exposing the identity of the person in the image that you are using as case-based explanation. And in a chest X-ray, that may not be that relevant, but for instance, when you are talking about the aesthetic evaluation of breast cancer treatments, you have a photograph of a woman's torso, and then that is clearly a problem. So the next work that I'm going to present was done in the context of a master's thesis done by Elena, and the goal was to anonymize these visual case-based explanations in the clinical context. So basically, we have a case-based explanation, and now we want to get rid of the identity while maintaining the explanatory evidence and having a realistic image. So the first approach was to try to look to the literature and try to find a generative model that would be able to be applied in this scenario. And we found out that this PPRL vegan was the most suitable one, which basically preserves privacy through identity replacement. So it's a generative adversarial network that comprises a conditional variational autoencoder as generator, and then a multitask classifier as discriminator, with this real fake classifier trying to help generate realistic images. Then this identity classifier that basically forces the network to generate an image with this replacement identity, and then a task related classifier to make sure that the anonymized version of the image also keeps the class. And then we basically compared this approach with some traditional ones like blurring and KSM select. And what we observed is that in certain contexts, it was quite competitive. In others, it was not that good, but like in images that shared the same pathology, the results were quite good. And I just must say that this was applied in the context of glaucoma recognition, and the reason for that was that this data set that we used had both biometric and medical properties, which was ideal to test our approach. And here I'm just presenting some results. So A basically represents the original image. B and C are the anonymized images using identities that share and do not share the original image's pathology. As you can see, like for images that share the same pathology, the results are a little bit better. And then D and D represent images from the average sets. And another thing that we tried to look was by generating these saliency maps, so these deep tailored saliency maps, we were trying to see if the image regions being used for the diagnosis were the same for the anonymized versions as they were for the original image. And like, so A and B have the same class. C was classified as not having glaucoma. And like, by looking to A and B, you can see that most of the regions are common, even though there are some differences. So in conclusion of this work, what we can say is that there is a need to improve privacy protection methods for medical data. And what we really want is to maintain the disease-related semantic features. So it's more than just keeping the class. We want to keep the exact same disease-related semantic features, because this is being used, or the goal is to use these images as case-based explanations. So they really have to keep the exact semantic features. But one thing that is lacking is realism. So that is one thing that we really have to improve in the next methods. And so starting from these conclusions regarding the first anonymization work, we came up with a second one that is that was published at IEEE Access, which basically tried to improve some of the drawbacks of the first model. And the first one was the replacement identity. So it was true that we were protecting the identity of the query image, of the case-based explanation image, but we were doing so by exposing another identity. So in this network, we just didn't use any replacement identity. Instead, we tried to approximate the privacy laws from a uniform identity distribution, so that it's like the identity recognition is kind of random guessing. We also used the Wasserstein loss plus a gradient penalty to try to improve realism, and we also used a mask reconstruction loss that tried to maintain all the disease-related semantic features. So as I was discussing before, we want more than just keeping the class. We want that the disease-related semantic features are kept in the anonymized version of the image. So now discussing the work that are currently being done, or some future work that we already thought about. So regarding like the MICAI work that I described before, the interpretability guided content-based image retrieval method, we also applied it to new data. So at the time it was with a data set. Now we also explored this method in a different data set, also with a different disease, this time pneumonia. And we also tried to have a more complete evaluation. So we also investigated other approaches to find the more appropriate feature representations for the medical image retrieval, for instance, by using attention mechanisms. And this is an article that is being finished. And another thing that we are currently doing, and it's kind of related with the first line of research that I was talking about, is to provide multimodal explanations. And more than that, to try to have explanations for more multimodal data. And in here, there is a master's thesis ongoing. And also, there is a work that is going to be presented this week at IPRIA, which is called Increased Robustness in Chest X-ray Classification through Clinical Report-Driven Regularization. And basically, the main idea here is to try to use the clinical reports to regularize the semantic space so that we can have better predictions and also more robust models. And that was shown both in terms of quantitative results and also in terms of quality of the saliency map generated. And this had to be done in a way that in inference, we only needed the images and not the clinical reports, because when you have a new image, you don't have the clinical report. That's basically what you want. And the other two lines of research currently being pursued. So one is to try to integrate some causal concepts into the privacy preserving approach. And that was a work that was submitted to MICAI 2022, and that we are going to know if it was accepted or not this week. And another one that is quite related with this anonymization process, but with a different goal. So in terms of this anonymized work, what we want is so we have a case-based explanation, and we want to generate a new image that maintains its properties while not exposing the identity. In terms of what we call here as biometrically morph case-based explanations, the idea is we have a case-based explanation, and what we want is to adapt this case-based explanation to the biometric characteristics of the query image. And that is particularly useful in the case of aesthetic evaluation, because so when a woman is going to have a breast cancer treatment, what we want is to look for similar patients in the past and adapt the result of the surgery or the treatment so that the patient the current patient feels more engaged with the result. So we want to find a case-based explanation, and then we want to adapt it to the characteristics of the current person, so that she can relate to that image, and then she can have more realistic expectations of how the result could look like. And for that, it's really important to have a classification network. That was not easy to develop for the aesthetic evaluation, because there are only a few images, and the aesthetics concept is a quite subjective one, so it was really difficult. But we were able to develop a successful network that basically is highly regularized, integrating a lot of prior knowledge and clinical knowledge, so that we are able to, in this new generative model, to keep the same classification label, and at the same time to find the most similar past cases in terms of the aesthetics. And so basically all the work that I presented here today was related with this Carnegie Mellon Portugal project called TAMI. Here I'm just presenting the goals of the project, and as you can see, they are very much related to what I talked about here today. So to have quantitative methods to objectively assess and compare different explanations, like here, the 3 C's of interpretability are one way of trying to do this. And then we want methods to generate better explanations, having variety, so like the complementarity of the explanations, adapting them to the consumer, and here also like this anonymization process or this biometrically morphing process is very much related to this. And then what we still didn't do much is about this explaining multimodal decisions, but it's one of the things that we are trying to work now. Now, just doing some small advertisement about some of the events that I'm co-organizing and that will happen in the next months. So one of them is Visum, which is a summer school that will happen in Porto in July. And here I'm just presenting the keynotes and the topics of the keynotes that we will have. So self-supervised learning, privacy-preserving machine learning, explainable AI, and also deep generative models. Besides these keynotes, we also have a project competition and also a mentorship program that we are starting this year. I'm also like one of the main organizers of the MICAI Hackathon, which is an event that will happen at MICAI in Singapore this year. And here we basically try to motivate the discussion in terms of how can we bridge the gap to the clinics. So there are a lot of methods being developed that are sold as helping clinicians diagnose or basically solving some of the problems, but just a few of these works are actually being implemented in the clinics, and we want to try to help reduce this issue. And finally, I'm also one of the organizers of this workshop on interpretability of machine intelligence in medical image computing. The submissions will start this week. No, sorry, the next week. So if you are working in this field, feel free to submit. And that's all. Thank you.
Thank you, Wilson, for this really nice presentation. I think we have a few minutes for questions. So please, if you have questions, you can either ask them directly to our speaker, or you can write them in the chat and we will read them for you. So while people are thinking of their questions, I have a curiosity about one of the last things that you spoke about, which is this work that you have submitted to MICAI. And I understood that you cannot probably say much about it, or you don't want to, but can you just explain why a causal approach would make sense for your privacy preserving algorithms.
Yeah, so maybe, yeah, it's not really like a causal approach. It's more like causally inspired, let's say. So we know that like the generated image depends on the identity and also on the disease. So basically, what we are trying to do is to have this relationship well defined, so that we can make transformations to one of these two modules, let's say, and that the generated image is easily manipulated by just changing one of these, and we are just trying to make those two modules independent between each other, so that by just changing one of them, we are just changing one of these properties and not the other. Yeah, but as you said, I cannot disclose much of this, but it's basically in this direction. So it's trying to have more like a causal structure in the generation of these anonymized images. It's not really a causal approach, but it's kind of tries to integrate these into a like the normal approach.
Okay, thank you. I think Francisco has a question. At least he has raised hand. So,
hello, Wilson. Congratulations for your work presented here. Thank you for giving me the voice here. So I am working with Explainable AI, but more in the part of in the front of human-computer interaction. So my purpose here is to address the topic of explainable AI with radiologists. I'm working with medical imaging also, and what I want to ask you is that if I take into account your research and go to a group of radiologists, what would you think that would be interesting to test as a user research like study, in your opinion? Like you talk about privacy, things like that. What do you think that you want to validate with radiologists, for instance, with clinicians, doctors, physicians, and so on? The things that you are researching here.
So yeah, I will. If I'm not answer it correctly, just you can interrupt me. So basically, the thing that I learned when I interacted with the radiologists were that they were more interested in kind of visual explanations than in verbal explanations. I think because at least from the point of view of radiologists, that's what they do. So they look to images. And so having a similar image makes more sense to them than having like a rule explaining why a certain case was classified in a certain way. And it was basically the medical image retrieval system that I talked about. So this anonymization didn't really arise from the radiologists, because as I said, so they have authorization to access these images, but there could be some other domains where these case-based explanations could be useful, but where exposing identity would be a problem. And one of them that I think makes sense is like, for instance, in a teaching context where you are trying to teach medical doctors to perform the diagnosis, and by having a system like this could help them, because they think a lot in a case-based manner. And another one is like, so medical data sharing is increasing, and we even have a company in Portugal that is called Tonicap that works that basically has a chat to try to, so where clinicians can interact and they can share medical data. And like, for instance, in the future, if they would like to integrate a system like this one, where you also would share case-based explanations, there is a clear need to anonymize them. And the other thing is when you are using images that are not like chest X-rays, but there could be photographs, like in the case of the static evaluation, where you have a photograph of a woman, and here there is like a clear leak of identity that you have to prevent. In terms of then like, and as I think, as you could see, like those systems, like those anonymized systems that we developed are not good enough at this point, mainly because of realism. So they are lacking realism. But when we are able to improve realism to a point where they could be that they could really be used as case-based explanations, then we would have to go back to the clinicians and try to show the images and try to see if those images are enough to convince them or to help them perform the diagnosis or the clinical decision. That could be more than just a diagnosis.
Okay, thank you for your answer. It was really clear answer. Thank you.
Thank you.
Guys, please ask questions if you have. I have at least, well, I have a couple more or even more, but I don't want to monopolize this. Anyway, I'd like to ask you, Wilson, because for me it was not clear. If the last model that you presented in the very, almost in the end of your talk, it seemed to be, you said it was a generative model, but to me it seemed more like a retrieval model, not this one. I think you are muted, Wilson, or at least I'm not seeing you.
I don't think I'm muted.
Oh,
I'm muted.
okay, yeah.
But which one?
The bottom one there.
Here?
Yes.
Oh, yeah, no, this one, yeah, sorry. Okay, so just to clarify, the model that are here, that I'm presenting here is not the generative one. Okay. The generative one is the one that we are trying to produce. So the model that I'm presenting here is the classification one. So it will be a module used by the generative model to basically to help. So because what we want is something similar to the one that I presented before. So it's very similar to the anonymized generative model, but this time we want just a different goal. But basically it will have the same, so yeah, as you can see here, for instance, in this one. So we want something similar to what is here. So we want to make it, to make the model produce realistic images. We want that the image that is generated has the same class as the original image. The only difference is that instead of trying to preserve privacy, we want to adapt the image so that it has the biometric characteristics of the query image. And this network that I'm presenting here will just be used to help the generative model reaches one of these goals. That is, we want to have the same image. And besides this classification property, this model is also being used to try to find the most similar images. And that's why there is like a retrieval component at the end of it. But this is just a classification model that will help the generative model. but the generative model doesn't exist yet.
And do you think that you have enough data to train a good generative model for this kind of data?
Yeah, that's the most important question. I'm not sure. I think it will be tricky, but yeah, we are trying to do it. We have more data now than we used to have, and I think that will help. But still, I'm not completely sure that it will be successful. But yeah, just one thing that I should mention is that this idea that I'm discussing here now, so these biometrically morphed medical case-based explanations, is also an Horizon Europe project that started in April. And so there are efforts being made to try to collect more and more data. And I think that will help. Because yeah, with the original amount of data that we have, yeah, it would be quite impossible to have this generative model as intended.
Okay, good luck then on that, of collecting more data. I think Gonçalo Oliveira wants to ask a question. Please, Gonçalo.
Yeah, I just wanted to ask, at the end, you mentioned that you are thinking of using attention mechanisms in your current or future work. Can you talk about what exactly are you trying to use them for in the light of the work you're presented today?
Yeah, so basically the idea was just to use the networks with these attention mechanisms to basically sorry, to I maybe move to here. So what we want is to have a disease classifier. So and then use this disease classifier to compute these features in the semantic space and then look for the nearest neighbors. And in the approach that I present here, we try to focus more the representations by doing this fine-tuning step. And we were just comparing with this step 1 model. So a normal CNN disease classifier that in this case was a DenseNet. And the idea was just to compare if, like, instead of using this DenseNet, if we use a network with some attention mechanisms in it, and then compute the features in this semantic space, if those attention mechanisms help or not, having more focused representations and representations that allow us to find the most similar examples.
So the idea is that by using these attention mechanisms, the saliency maps would be more informative in some way.
We are not computing, yeah, that could be an option, but we are not computing the saliency maps. We are just like comparing the CNN disease classifier without the attention mechanisms with some other model with attention mechanisms, and then computing the semantic features and the distance between them without looking to these. So without generating these saliency maps with the attention mechanism network. But regarding that, and I think there is Tiago here. Tiago, are you here? Or not?
Yes, I am. Yes, I am. I am here.
Yeah, maybe you want to have a comment regarding the like attention and the saliency maps, because you also did a work in this direction.
So I perhaps can add something. So one of the main ideas here, so the intuition was that if we are using attention mechanisms, in the end, the quality of the saliency maps would have more significance. So this would be the intuition. So we used the model. So we did not build the attention model. So we used an already established model that was used for, if I'm not mistaken, eye images, I guess. So that paper that uses spatial attention and channel attention, and our intuition was this one. But in the end, the results show that the methods based on solely only on post-hoc methods work slightly better. And we also have been studying these attention mechanisms in the group to see if they are actually working as the papers are, let's say, selling them. So the papers sell that just by using attention you would achieve automatically interpretable models, but perhaps that may not be the case. But the work was pretty much as that, and so we did an application to this use case with Wilson.
I see. And the name of the attention mechanism, was it CBAM or something like that?
Yes, yeah. So that paper is based on CBAM, but perhaps later I can share you the original paper that applies that to the eye, because it was a very specific paper that Professor Jaime at that time shared with us. But yeah, it was pretty much based on CBAM, yes, exactly.
Okay, thank you.
Yeah, thanks, Tiago.
So maybe attention is all you need.
Or not.
So I think we are running out of time. So if there is another question, we still have time for one more question. Otherwise, well, there seems to be no questions. More so, again, thank you all for your presence, and a very special thanks to Wilson, and now also to Tiago for these final remarks. And we hope to see you again in 2 weeks. And yeah, that's it. You are always welcome to come to these Priberam machine learning lunch seminars.
Thank you, Diogo.
Thank you.
Thank you all.